Hi, welcome back. Now is the time that we're going to get really stuck into the meat of machine learning. Things like overfitting, bias, variance, regularization, penalization. These things are at the heart of all supervised machine learning. We're going to take it slowly with an introduction using something called polynomial regression. So here goes. Let's have a think about how we might do linear regression with a complicated function. What might a complicated function look like? Well, imagine it was something like this, some kind of sine curve. So here was your x, your independent variable, and here is the target variable, y. What would you do? Something like that? Maybe, I don't know, you would try fitting it down that part over there. That's not a very good line. Down there. Whatever straight line you fitted, it would just not work. So what on earth do we do? To put it another way, if you try fitting this with y equals beta naught plus beta 1 times x, it is literally impossible. As we said, you might get, I don't know, you can't do it. So what can we do? Well, what we can do, actually, before moving on, what I should say, I think I have said previously, this x value, which might be something like lot area, that is called a feature of our example. So if our example is information about a house, each piece of information about a house is called a feature. Lot area is a feature. Number of kitchens is a feature. Every piece of information is a feature. But we can also create our own features. So imagine we have lot area. If we took lot area squared, that would also be a feature. Let's add lot area squared into our model. We have now engineered a new feature. What kind of model can we now fit? Well, of course, you remember that the graph of x squared looks something like this. So the graph of minus x squared looks something like this. So now that we have x squared in our model, forgetting the linear term, we could probably fit a model which goes like this. Now, it's still not fitting our data very well, but it's possibly better than it was before. Each new power of x that we introduce into our model as a new feature allows our predictions to get more and more complicated. If we just had x, all we could fit was straight lines. Once we had x squared in it, we could fit something like that, or something like that. Once we have x cubed, we can fit something like that, or with the negative coefficient, something like that. And as we put it all together, we can fit increasingly complicated shapes. So going back to our original data, which was some kind of sine curve, if you had enough powers in your polynomial, you could probably try to fit this kind of shape. That's polynomial regression, adding lots and lots of powers of x in order to be able to fit complex relationships between the original feature, for example, lot area, and the target variable. In a minute, we're going to head over to Python, and what we're going to do is we're going to simulate some data, which is indeed some kind of sine curve, but we're going to add some noise into the data. So instead of a nice smooth curve like that, we're going to get thousands of points spread around the curve. The Apple Pencil isn't too keen on doing dots on the screen, but you can imagine just thousands of kind of slightly noisy points. And when we fit our model, we're not going to make available to ourselves all of the points. We're just going to imagine we have a somewhat limited data set with a few points. We're then going to use polynomial regression to try and capture this underlying relationship. We're going to see how well we can do. So here goes.